Okay, sorry about that recording snafu, but you didn't miss much. All right. While Eclipse is starting again, I hope it works this time. Let's think about the case. What happens when what do we do when there isn't room to grow in this new world? So we're going to be coming along and our data, first of all, how will we know that there's no room to grow? Right, well, data.length will equal length. So the length of the array will be the same as our length instance variable. Now, if that happens, what do we need to do? Let's suppose it's filled up. So this now contains 8 things, and our length is 8. We've got to make a new copy like we did before, but what's the difference from the time before? Twice as long. And then once we've got room to grow, we can add like before. Okay? So let's, we'll do that shortly. Okay? What about the size method? What will it look like? If someone asks, what's the size of this list object, what will we say back? Well, we can find out in Man, this is like a nightmare. Hold on. I'm not easily deterred. All right. No, it won't write. Come on, give me a break. Maybe. Let's see. Wow. Okay. I'll remember that next time. Thank you very much. All right. So this is what we concluded. Data sub length equals val length plus plus. That's what you do if there's room to grow. If there's not room to grow, we need to detect that. So we say if data.length is the same thing as length, we decided we had to say data gets arrays.copyof, and we're going to ask it to copy data, and we want it to be twice as long as it is now. So it'll copy down to something twice as big, and all the extra space will be on the right end. Do we need to do anything about length inside this if? Has the length of the list changed when we made this copy? The size of the array has, but has the length of the list? No. So we don't have to change that. And then if we do this, now there's room to grow. If we don't do that, there's already room to grow. In either case, we do that. What's the length of the list? It's just length. Okay? And set and get are similar as they were before, but there's one difference. We have to work a little bit harder for the exceptions. So this won't quite work. If we say data sub index, return data sub index, what's wrong with that? Someone says, give me what's stored at index 7, so we return data sub index, and if the index is out of bounds, we throw the exception. The array throws the exception. What's wrong? Yeah.
They could call for an index that is within the length of the data array.
Okay.
It's not within the length of the list.
Okay, so if we have this situation where we have an array with room to grow, and let's say it has 1, 8, 7, 2 in it, and someone asks for the element at index 0, that's good. We'll give them back 1. If they ask for the thing at index 3, we'll give them that. But what if they ask for the thing at index 6? This one here. We can't give them whatever garbage is stored in the array. What do we need to do if they ask, and I'm assuming that its length is equal to 4. So what should we do if they ask for the element at index 6? We have to throw the exception explicitly because it's not going to be thrown by the array. So get ends up looking like this. If index is less than 0 or index is greater than or equal to length, we throw the exception. If we don't throw the exception, we return the data element. And the same thing happens with set. We still got to do this check on the index. And if we don't throw the exception, we just say data, just like before, data sub index gets val. Okay, so let's see, which project are we in right here? We're at list 2, so I'm going to run my list test and make sure we've implemented that correctly. That's good. And now, how long did it take last time to, okay, a little over 14 seconds. And how long did array list take? About 1/100th of a second. So hopefully we'll be somewhere. I doubt we're going to beat array lists. I don't know. But I bet we'll do better than 14 seconds. So I'm going to run the list timer on our new implementation. Okay? So it's slightly worse than array lists, but you know, they worked on it a lot harder than I worked on this. Just that simple change, which required a re-implementing the whole class, massively speeds it up. Makes a huge difference. Yeah.
What's the stop us from going, instead of starting with 2 and multiplying by 2, so I'm starting with 10 and multiplying by 10?
Okay, so he's asking, okay, I started with 1 element and doubled each time I ran out of space. Why not start with 10 elements and double and multiply by 10 each time I run out of space? Or why not start with 1 billion elements and I will hardly ever run out at all? So there's a trade-off. What's the trade-off here? Yeah? Memory. So yeah, if I'm willing to waste a huge amount of space, like if I put 1 billion elements into my array to start with, then I can make adds really fast. But I'm wasting a lot of space to do that. So what I did is sort of a reasonable trade-off between, hey, I'm wasting some space, but I'm not wasting a huge amount of space, and I'm getting a good return on my investment. Now, it turns out that you can learn how to analyze these algorithms. The first way we used it is called a quadratic running time. That's something you learn about in the class like 2420. So quadratic running time means that if as the length of the list doubles, the time it takes to do an add quadruples. So the longer the list gets, or the average time it takes to do an add. Most adds are fast, but every now and then there's one that's really slow. But the average time, to do an add into a 1,000,000 element array, well, is about 4 times the time it takes to add into a 500,000 element array. That's what that's saying. On the other hand, the new situation that we have with the faster implementation is linear, meaning that if you double the size of the list, it doubles the average amount of time to do an insertion. No, in fact, that's not even right. It's constant. Yeah, the way I've got it is constant. It doesn't matter how long the thing is; the average time is always the same. Right? But that's a topic for another semester. So the last thought I want to leave you with here before fall break is this. you're gonna finish PS6, and then you're gonna go off and take fall break. And then you're gonna come back, and we're gonna have a week of reviewing for the exam and taking the exam. And then you're gonna be doing PS7, which is gonna involve implementing classes like we've seen here the last couple of days. And it's gonna seem like ancient history to you, because you're not gonna be reviewing it for the exam, because it's not on the exam. So just take a minute. If you ever write anything down in your notes, just write something down to remind you that when it comes time to do PS7, you need to come back and remember what we did this week. And a really important idea I want to give you, a takeaway, is the power of keeping instance variables private. If you don't remember anything else, I want you to appreciate what we buy by making the instance variables private. Because if we don't, this will be the last thing I show you. Let's go back to my list. Let's look what happens if we make the instance variable public. Right there. Nothing, the class will still work just fine. But if we go back to the class that uses it, all right, this is what I need to change to public. If we go back to here, now I can do stuff like list2.data. I can directly access data if I make it public. And once you have your clients, I don't know why it's complaining there. Anyway, once you have your clients able to do that, you're going to have great trouble ever changing your internal representation. You need to keep the internal representation private so you can change it. That'll be on the final. That's the second question I told you to be on the final. The reason we keep the representation private is so it can be changed. That's the main reason. Okay, have a great fall break. See ya in a couple weeks.
I was just curious, the story with the book, that doesn't happen to be the textbook that you wrote.
Yeah.
Is it the intro to the scientific opinion? Yeah. Oh, now I got a story to go with the book on my shelf.
Yeah, I used to get those migraines a lot more frequently. I haven't had them in a long time.
Yeah, I'm surprised you didn't get one today.
I had one when I was in the outfield of a softball game once.
Oh.
That's not where you want to be.
No, not when it's in front.
No, you can't see
yeah.
that.
Just hold up the glove.
Yeah, I had to get out again.
Can I ask you a question about this?
Sure. Oh, hold on.